All right, recording has started. So the first hour will be revision, exactly as we did in the lecture. So the first lecture was revision and the second lecture was 3D stress transformations. So for this tutorial, first hour will be revision, second hour will be 3D stress transformations. All right. So let's start by solving question 1 of the revision topics. We need to draw the free body diagram for the beam, this one, and the man under these conditions, and find the reaction forces. Now, I will draw this on my digital paper, so you can take your time to draw your own as well. So this is question 1. So, revision tutorial. Question 1. So the man has a mass of 75 kilograms. I call this capital M 75 kilograms, and the beam itself has a mass of 40 kilograms. We want to find the reaction on the beam at C. So we want to find the reaction forces at point C. Let me also draw points A, B, and C. And so this is what you should have on your screen. Yes, Joe, I was just writing on it, and I needed to see all the data as well. If I share it, I don't see the question. So of course we have here the pulleys. These pulleys are of course pinned in place as well. This is a very crude representation of a man on the beam. And we know that this man is of course holding onto the rope, and it is exerting a force on the beam. The force on the beam that it is exerting is of course its own weight, and the beam is reacting with a normal force on it. So let's start by doing the free body diagram of the man. That means we have to isolate the man from the beam. If I do the free body diagram of the man, it looks something like this. And how many forces are acting on this man? Come on, how many? So there would be the pulling force. Will it be down or up? The tension of the rope. Will it be pointing down or up? Up. Why?
Because the rope's trying to pull him up. So.
Exactly. So we are doing the free body diagram of the man. So the man is tugging down on the rope. That means that the rope is pulling up on the man. So this is the free body diagram of the man. That means the tension of the rope. Let's call it the person to be inclusive. And the tension force of the rope is, of course, pulling up. So let's call this T. What other force we have are acting on this person? The weight, because see, this person has mass. So there will be an active force applied here in the middle, well, at the center of gravity of the person, of mg, where m is capital M, because that's how I call the 75 kilograms mass. And there will be a reaction force course, a normal force from the beam. Which direction will that take? It can only be up because, okay. All right. Do we have an indication on how long the arms of this person are? See. No? Yeah, apparently we don't. I mean, it doesn't look like. Yeah, we have no idea, and it's not given anywhere. So that means we can assume that all these forces are collinear. So they act on the same line. So although they don't look like they act on the same line, since we have no indication on how far away that T is, then we can say, okay, these forces are collinear. So let's assume forces are collinear. That's it. This is the free body diagram of the man. Now let's do the free body diagram of the beam instead. So I'll just draw the beam. Of course, free body diagram of the beam means I have to remove the man and cut here the rope as well. And so I have, this is point C. This is point B. This is point A. So in A, how many forces are acting on this beam in total? Let's start with A. In A, which force do we have in A? Well, if the man feels a normal force from the beam, that beam also feels a normal force, the same normal force from the man. It's the same magnitude, but it's acting in the opposite direction. Because when I reconnect the man to the beam, these two forces cancel each other out. Agreed? That's how it works. Now we have the rope here. And what is the tension in this rope? Is it T or is it a different one? Look at the arrangement of the pulleys. Yes.
Would it be mg?
What do you mean mg?
Would the tension be equal to mg? Big M.
This one?
Yeah.
Or the, no. Okay, because the tension will come from the free body diagram of the man, which is mg minus n. So you see, it has to do with n as well. So if there was no n, then yes, T will be equal to mg. But since there is n, that's not true. Okay, so what do we put there? Eva asking, is it not just not mg? No, it's not just mg now because there is also n. Alessandro, see this? So we have T, we have mg. If n was not there, then T would be equal to mg for equilibrium. But in this case, no. No, we can't put mg instead of n at A because this man is propping himself up by doing so. Okay? Yeah, it's a bit more involved. So if this was just standing on it, then yes. If there was no T because it wasn't holding onto this rope, then yes, mg would be equal to n, and you would be right, but not in this case. Let's see at B. At B, we have this rope, so it has to do with T. But is it T or is it a different number? Sorry, Eva was asking, can we assume the man is a point mass? Yes, because we have no information on the geometry of this person. So yeah, we can assume it's a point mass. Come on, guys, this is first year stuff. Remember when I told you 2 years ago now, well, almost 3 years ago, that if you have a pulley, with a certain tension T, let's call it T1, and another tension, let's call it T2, are these T1 and T2 the same or not? T is the same. Okay, why? It's the same under certain conditions, okay? Because it's the same if the pulley is massless and frictionless. The pulley is massless and frictionless, and the cable is inextensible and massless. So in this case, imagine if you have a pin here. So if I do the equilibrium around Z, so around point O in the Z-axis, for this thing, I get, let me do this lighter, I get T1 times the radius of the pulley, counterclockwise. So plus T1 times the radius of the pulley. That's the moment. Minus, because it's clockwise, T2 times the radius of the pulley. For equilibrium, this must be 0. And so that means that I can say that T1 is T2. And that's the case if you have no friction and no mass. Because if you have mass and that pulley is rotating, you have to take into account the acceleration of the acceleration of the pulley. But the pulley is massless, so there is no acceleration. And if you have friction, you have to take into account all the friction that is going on around these two angles. So this angle here, always in the middle, let's call this theta. This angle here must be taken into account if you have a friction. And if you have a friction, this equation becomes the capstan equation. Did you know what a capstan is? You know what a capstan is? Have you ever sailed? No? So on boats, or on ships, actually, there is something that we call a capstan. Yeah, broad revolving cylinder, something like this. You should probably have seen this already. So this thing, see, with the rope around it. And so the capstan equation looks like this. It says that the T load, so the tension of the load equals the tension of the hold times E to the power of the friction coefficient times theta. So you have, so this T2, what I'm saying, is exponentially growing with the angle. So if theta is 2 pi, T2 is much larger than T1. But theta can be 4 pi, 6 pi, 8 pi. So I can do 1 turn, 2 turns, 3 turns, 4 turns. So as many turns as you make, you can hold a larger and larger load with a tiny force. That's why the capstan is used to actually harbor ships. So you have large ships that can be just harbored quite easily by a couple of men only. You have huge amount of mass that can be just harbored by a couple of men using a capstan, a couple of capstans, as you want to. Okay, so that's quite interesting. So you probably also have heard about the capstan equation. Well, if you haven't heard about the capstan, you don't know about the capstan equation. But the capstan equation is this. Yeah, this is how you find it. Yeah, that's what I was saying. T2 is T1 E to mu beta, where mu is the friction coefficient. And as you can see, if you have no friction, the friction is 0, T2 equals T1, because e to the power of 0 is 1. So everything makes sense. All right, let's go back. So we have that this T is the same along the entire length of the rope, because we are assuming that everything is frictionless and massless and so on and so forth. So this is just T. And the beam has mass. Where is the weight of the beam applied. Let me check if we have the dimensions of the beam. Yes. So we know that point B is also the center of gravity of the beam. Okay, and this is 1.5 meters. Let me write it down. 1.5 meters here. We have 1.5 meters and 1.5 meters. So we have a weight force of applied at the center of gravity of mg. Now, in C, what kind of support is that in C? Eva asking, how do we define the center of gravity for different geometries? Well, you will need to, so there is a way to find the center of mass of any geometry, and it has to do with the first moment of area. Remember that? No? Yeah, first moment of area. It's also called the static moment. So in order to find the coordinate, the x coordinate of the center of gravity, you need to integrate y in the m and divide everything by the mass. Okay. So, well, this is, and if you want to find y, you have to take this. You just have to exchange coordinates. But of course, if you have to do with things that are symmetric, so if you have symmetric shapes, the center of gravity is, well, provided that you have constant density of your shape. So at constant density, the center of gravity is always on the axis of symmetry of the shape. So in this case, it's this. If you have a circle, of course, it's the center. If you have a rectangle, you can take the diagonals. Okay, so you can find it's always the center of the shape if it's constant density. Okay. So you have to remember these things. I mean, unless you have a project, an individual project which entails complex geometries for which you don't know where the center of gravity is. But in that case, it's also easy because you have an FE model of that generally. And if you, any finite element software will tell you exactly where the center of gravity is for a particular shape, and it will tell you the second moment of area, the polar moment of area with respect to any axis that you want. Okay, so it does the calculations for you, basically. So you have to solve integrals, but if you have FE software, which is just basically you divide your shape into tiny cells. Each cell can be easily calculated, and then you sum them all up. That's the idea of Riemann integration anyway, and so that's how it goes. So I was saying this is a pin joint. Did you say we are doing FEA this semester? No, you did FEA last semester. You do 333 MA? That was FEA. But you might need to use FEA for, well, 90% you will be using FEA for your individual project or group project. And there will be a component of FEA in the coursework here as well, the coursework of 326 and 340. Small component, not very complicated. Okay, so pin joint. How many reaction forces we have at the pin joint? 2. So we have, let's call this CY and CX. Let's also define a reference frame. Since I've used Y and X, now I have to tell you what I'm saying is Y and what I'm saying is X. Okay, because if I don't tell you, then you have no way of understanding what is X and what is Y. And of course, we have the Z-axis, of course, is in this direction, which is counterclockwise rotation positive. Okay, now we can use the equilibrium equations. Remember, equilibrium equations are the sum of forces equal to 0, and the sum of moments about any point equal to 0. Now, these are the vectorial equilibrium equations that we are in 2D space, or sorry, in 2D plane in this case. So these ones are 3 equations, 3 algebraic equations. They are the equations that you always used. Now, do you want to use any particular point for this last equation? See the sum of moment about P. What is P? P is any point. So that means we can use A, we can use B, we can use C. Of course, there is a particular point which is easier. Which one?
B.
Why B? What are the unknowns in this problem? So Cx and Cy, for sure, but we also don't know N and T. So all the unknowns in a problem like this are the reaction forces of and the internal forces. I put them on all in red. Everything that is red is unknown. Okay, so see N, T, Cx, C, Cy, or T and N here. So we have 4 unknowns, but we only have 3 equations. So what's the problem? Yes.
Well, first, it's hard to do it with like more unknowns with less equations, but would we not take moments from C since there's 2 unknowns there?
That is correct. So the best way of doing it, of choosing this point, is to find the point where you have the most unknowns. So if I choose point C, the moment of Cx and Cy will not appear in the moment equation because they are passing through C. If I take the moment about B, T and Mg will give no moment about B, but then I have 1, 2, 3 unknowns. Well, this one no, because it's still passing through B. So see, C and B and A are, I'd say, equivalent because Cx is passing through A, B, C anyway. But let's choose C, just because. So let's take this one. And let's say along X, along Y, and around Z, around point C in particular. So along the x-axis, we only have Cx, which I drew in the same direction of the x-axis. So it's positive Cx equal to 0. That's it. And for the y-axis, we have negative n. See, n is going against the y-axis. So positive t, negative n, negative mg, positive cy. So let me draw this. It's minus n. In order, this would be minus n plus t minus mg plus cy equal to 0. Yeah. Oh, sorry. Let me just. And moment equation. Remember, moment is, what is a moment of a force about a point? Is the, yeah, what's the matter? Oh, the screen is gone. Okay. What's going on? Just a second, guys. Why around? Come on. Yep. There you go. Solved it. So I was saying the moment equation, remember moment is force times perpendicular distance, or if you want to be more rigorous, remember that the moment equation, to find the moment of a force is always the vector moment of the force is the position vector of that force cross product the force vector itself. Okay, but this boils down into force times perpendicular distance always. So let's use this one that we know how to use. And so we're talking about C. So what is n? What is the moment of n? It's force n times the perpendicular distance. So vertical force times horizontal distance. Agreed? So this is 3n. Positive or negative? Why positive? It's correct, but why positive? because n around C rotates counterclockwise, and we said that counterclockwise is the positive direction. They should detect the motion if you move around it or no. Okay. And what about T? So is T positive or negative? Negative moment. So it's minus T times 1.5. So minus 1.5 times T plus 1.5 mg, of course. And then that's it. There is nothing else. So let's count the unknowns. 1, 2, 3, 4. This is the second unknown. This is the third unknown. And that's it. We have 4 unknowns in 3 equations. What's missing? There is another relation that we didn't explicitate in formulae. It's there. It's on the screen. It's the free body diagram of the man, because that also contains a relationship between T and N, which are 2 of our unknowns. So from the free body diagram of the man, this is free body diagram, not here. So this is free body diagram of the beam. And if you do the same for the free body diagram of the man, let's call it person. Let's call it VIP. You have that, of course, nothing is happening in the x direction. Everything is happening in the y direction, which is T minus mg plus n equals 0, capital Mg. And then on the z axis, let's do it around the center of gravity of the man. Well, we assume that these forces are collinear, so nothing is happening there as well. Okay? And so this one is the second unknown, no, the third unknown and the second unknown. So now we have 4 equations, equation 1, equation 2, equation 3, equation 4, in the 4 unknowns. Can you solve this? Of course you can solve this. It's very easy to solve this. Shall we see if we can solve this with MATLAB? Well, really, the first equation is used. Well, the first equation is solved already. Cx equals 0. That's it. Don't need anything else. So let's solve equations 2, 3, and 4 with MATLAB. See how do we do that? So let's solve equations 2, 3, 4 with MATLAB. So with MATLAB, I would take, so I have to use this approach here. So AX equal B. Do you know how to solve this system? Where A is a matrix. A times X equals B. Do you know about this? So you can solve by X. X is equal to the inverse of A times B. You agree with me? So this is how you do it with MATLAB. Now, in our case, equation 2, let's say that X is N T C Y. N T C Y. So it's a vector of 3 elements, 3 unknowns. So that means that our A matrix is, so first N, then T, then CY. So in equation 2, we have minus 1, plus 1, so minus 1, plus 1, and CY, plus 1. That's equation 2. Then in equation 3, we have 3 minus 1.5, and 0, because there is no cy. And then in the last equation, we have 1, that's n, t is 1, and then 0 again, because there is no cy. Agreed? So this is A, and then B are the terms that didn't fit in the other side. So of course, this must go on the other side. So in equation 2, we have mg. In equation 3, we have 1.5 mg, sorry, minus 1.5 mg. And in equation 4, we have plus capital Mg. Okay, so if I do this in MATLAB now, I can just copy this thing into MATLAB, if I can find it. Where is MATLAB? There you go. And I can say that matrix A is minus 1, 1, 1, 3, minus 1.5, 0, 1, 1, 0. Okay. B is M was 40 times 9.81. Yes, this must be a vector though, must be a column vector. So this, comma, minus 1.5 times this, comma, 70 times 9.81. Is it 9? 0. No, 9. 9.81 transposed because we want a column vector. Okay. And now I can do that x, which is my unknown vector, is the inverse of A times B. Bam. These are the answers. Okay. So the first answer is N, the second answer is T, and the third answer is CY. Does it make sense? Or even better, you can use this notation because MATLAB doesn't like the inverse of A, so you can use this other notation here. So A backslash B, which means B divided by A. Okay, and it gives the same. In this case, it's a 3 by 3 of very simple number, so it gives you the same result. But if the matrix A is ill-conditioned, so it has some issues inverting the matrix, this second approach is better than the first. Okay, nice. We have learned one more thing. Okay, so that was question one. So now let's solve question 3. Which is this. The beam shown in figure Q3 is subjected to a point load of 4.2 kilonewton and a distributed load of 3 kilonewton per meters as shown. The cross section of the beam, Joseph schools. Okay. Cross section of the beam is a T section with the neutral axis position given here. So we know where is the neutral axis with respect to the top flange or the bottom fiber of the beam. Sketch the shear force diagram showing significant values. Sketch the bending moment diagram for the beam showing significant values. Calculate the maximum tensile stress and the maximum compressive stress in the beam due to bending, clearly indicating where they occur. So on this section, so we can already find out, imagine on this beam, we have to find the bending moment diagram to check where is the largest bending moment. Now on that section that looks like this, which point on this section is the most critical, is the most stressed? What do you think? Which one? A point here on the neutral axis? I'd say no, because that's for bending moment. What is the flexure equation? What is the stress equation for bending? Sigma equals m over I times y. So m is constant, that's the bending moment. I is constant, that's the second. So depending on where I am vertically on the section, So the farthest away I am from the neutral axis, the larger is that y. And so which point is the most stressed? Of course, if I am here, y is 0. Say left hand, no, it doesn't look like that because this is the x-axis. So y is the perpendicular distance from the neutral axis. Okay, so it's either top or bottom. Which one is the most stressed? The bottom one, because it has the longer way to go. This is 99.6, this is 60.4. So this y is larger than this y. And what about left or right? Does it matter? See, there is only y. There is no x involved. That means it doesn't matter. All right? Well, in this case, x is here, so it should be z, y and z. One is y, this is y, and this one is z. All right? So let's do this. Very, very, very easy. I mean, it's very easy in principle, but it's quite long. Let me see if I can make this. So let me clear this. And let me draw this beam. So this is question 3, we said. Question 3. Let me draw the beam here first. And then, so let me put it so I can see it. So, yeah. So while I draw this, you can draw this as well. I need this on top, otherwise. So we have 2 meters away. So 2 meters away, there is a pin in A. Then 5 meters away ends the distributed load. And 3 meters away, there's the end of the beam with the other pin, B. And so I have the force, 4.2 kilonewton force. Then I have a distributed load of 3 kilonewtons per meter. And I have the 2 reaction forces that I can find easily by doing the free body diagram. So let's call this AY and BY, the reaction forces at B and A. Okay. So first of all, we have a distributed load. How do we treat a distributed load? You can find the equivalent force, the force that is equivalent to that distributed load. So the equivalent force is, of course, passing through the centroid of the distribution, which is that point there. So the equivalent force is 3 kilonewtons per meter times 5 meters. That gives 15 kilonewtons. You agree? That's it. And now we can just solve this for x and y. So on the, well, the x-axis has no forces. So I'll just take into account y and z. Which point would you like to choose for the reduction of moments? I think it doesn't matter. Let's choose A. So we get rid of AY in the moments equation. So Y, we have minus 4.2. I'm doing this all in kilonewtons. Minus 4.2 minus 3 times 5 plus AY plus BY equals 0. Do you agree with me? It should be quite easy. So two equations, one unknown. So we need the other equation to solve it. 4.2 goes counterclockwise around A. So that means 4.2 times 2 minus because this force goes clockwise around A, 15 times 2.5. Can you see why it's 2.5? Yeah. And then we have 8, no, this is 3 meters. So we have 8 times BY. And that's positive because it's also counterclockwise. Agreed? Good. Now, from this one, we can find unknown 2. And from this one, and then we solve this first, and then we solve this. Now, I have a solution already. And AY and BY are, this. So AY and BY are, AY is 15,562.5 newtons. And BY is 3,637.5 newtons. Okay, so this is out of the scope for this tutorial. Of course, this is just simultaneous equations. You should know how to do this. Now, how do I draw the shear force and bending moment diagram of these? I need to find the internal forces. How many segments I need to study this beam? Remember, cut, look left, cut, look right. So I had one student telling me 2 segments. Is this correct or not? Remember how to find how many segments you need? So from here to here, nothing is happening. So that's segment 1. Then suddenly, 2 things are happening. There is this distributed load that comes into existence, and there's suddenly AY applied as well. So I must stop here. From here to here, that's segment 1. Then segment 2. If I start from here now, just on the right-hand side of the distributed load, then I can go on, and the distributed load is there. Okay? It's continuously distributed, so nothing is really happening suddenly. Remember, this equivalent force is not there. The equivalent force is there only for equilibrium. But in reality, there is a distributed load there. But then we get here, and the distributed load suddenly ceases to exist. And so that means we must stop here as well. So we have segment 1, segment 2, segment 3. So we need to study this into 3 segments. And for each segment, you cut and look left, or you cut and look right, either of them. So this one is segment 1, segment 2, segment 3. Segment 1 goes from 0 to 2 meters. Segment 2 goes from 2 to 7 meters. Segment 3 goes from 7 to 10 meters. And so let's see, cut and look left. If I cut here in segment 1, do I look left or right? What do you think? Well, it's much easier if I look left, because if I look left, I only have this. If I look right, I have another, I have so many things going on the right. So let's look left. Look left. If I look left, I have to draw only the chunk of beam that is on the left. Okay, so this is where the force is applied, 4.2 kilonewtons. And remember, I have to also introduce the internal forces N of x, V of x, and the bending moment, M of x. Following the convention, remember the convention? Let me remind you of the convention. convention for positive internal forces are normal forces in tension, shear forces like this, and bending moments are smiling. Okay, so since I'm looking left, I have to expose these forces on the right. So I have to draw them in this way, and that's what I did. Okay. Now, if I do equilibrium of this, x, y, z, in the x direction, I have that n of x equals 0. Okay, there is no normal force. Makes sense because there is no acting horizontal force. In y, we have minus 4.2. Let me do this in green. Minus 4.2 minus v of x equals 0. Do you agree? So that means that v of x is minus 4.2. So let me draw this. Let me do this exactly as it is. So v of x is minus 4,200 newtons. Constant. Constant. It doesn't depend on x. It doesn't matter if I am at 0 or at 2. So this segment is only valid between 0 and 2. If I'm at 0, v of x is minus 4,200. If I'm at 1, v of x is minus 4,200. If I'm at 2, minus 4,200. Doesn't matter because it's constant. What about the bending moment? Well, the bending moment equation is m of x is positive because it's counterclockwise. And this distance, remember, this distance is always x. And so, and then you have the positive again, so plus 4.2x equals 0. Agreed? So that means that m of x is minus 4.2x. So if I solve this, kilonewton meters. Okay? Nice. And now I can start drawing it. I can already start drawing the bending moment diagram and the shear force diagrams. So I'll do this. I'll need it. Yes, I need it a bit like that. This is x. This is m of x in Newton meters. And I'll also plot on the same graph v of x in newtons. So see, v of x is constant. It's constant and negative. So v of x is this. Let's say this is 2. Now we have 7. Now we have 10. So segment 1 is this one, from 0 to 2. This is segment 2, and this will leave. This is where segment 3 lives. So I can only draw this function between 0 and 2, because that's where segment 1 exists. Then I draw this function for the bending moment, which looks like this, more or less. Okay? And I can find how much is this value. How much is that value? Well, it's minus 4.2 times 2, which is 8.4. So minus 8.4. What are the units? No, 4.2 is kilonewtons. So in this case, it's kilonewton meters. Since we want it in Newton meters, the answer is minus 8,400 Newton meters. Okay, well, we don't need to put it here because the units are already here, so it doesn't. Okay, minus 8,400. And this one is, of course, minus 4,200. That's it. We must stop at 2 because that function that we found is only valid between 0 and 2. Now we can find the other one. The other one is inside this segment, I cut at a generic point, and I can look left or I can look right. Which one's easier? I think it doesn't matter. So let's look right, because I want to show you something that you should remember, which is, well, if I draw everything that is on the right of this, I have to draw a chunk of load. So let's say it goes from here to here. So this is where the cut is. And I have to draw here a chunk of load and by. So by, this one is 3637.5 newtons. This is 3 kilonewtons per meter. 3000 newtons per meter. And of course, I have to use the other convention, which is this is n of x, this is v of x, and this is m of x. Okay? Now, the important thing is that I want to show you is that what is this distance? How much is this? This x? No, because x is the distance from the start of the beam to the cut. So this is x, because it's from the start of the beam to the cut. This is not x, because there is no start of the beam. We are already at the cut, and this is the end of the beam. So how much is this distance? Well, if I sum this distance to x, I get 10. So this distance is 10 minus x. Yes, correct, Eva? All right. Okay, but I need another distance yet, because if I need to find the equivalent force of this load, I need to find how much is this distance here. How much is that? Remember, this is 3 meters. So how much is that? 10 minus x minus 3. So 7 minus x. So this distance here is 7 minus x. And now you can just do exactly the same thing and solve it for the other part. You can find the 3. Well, let's do just 2, because n of x is 0. Of course, we have no n of x. We can find that v of x, I have a solution here. So that's up to you to find out. V of x is minus 3, 7 minus x plus by, whatever that is 3,637. And minus m of x minus 3 times 7 minus x squared divided by 2 plus by times 10 minus x equals 0. Now look, this is the equation of a straight line. So by is a number. Okay, remember that? So it's not an unknown, it doesn't matter. I'm writing by instead of 3,637.5. So this is the equation of a straight line. And this is the equation of a, what's with the square? Okay, it's a parabola. How many points do you need to draw a straight line? Euclid says 2. As long as you have 2 points, you can draw a straight line. What are the points? So v of x is the line that we have to draw. So we can draw v of 2 and v of 7. So the end point of the segment, which are also the interesting points. They can help us drawing that straight line. What about the parabola though? How many points do you need for the parabola?
3.
3. Any 3? Well, any 2 points, but you also need to know where is the maximum or minimum. Okay? Remember that, so I will not do anything with S3. S3, you do it yourselves. Remember that the derivative of the bending moment is the shear force diagram. So how to find the maximum or minimum of a function? You take the derivative and set it equal to 0. So the maximum bending moment will happen where you have 0 shear force. That's a neat thing, because if we draw this, I'll find out that V of 2 for segment 2 is 11,362 here. And the at 7, this is minus by, okay, which of course is this one. This is minus 3,673.5, whatever. So you get this. This is the straight line. See, there is a jump here. Jumps up. How much is this jump? What's happening at 2? At 2, AY is there. AY is 15,500. AY is 15,500 means that the shear force passes from minus 4,200 plus 15,500, jumps up to 11,300 and whatever. So this jump is exactly the value of AY. And then it goes down. And then we must stop because that's it. That's the end of the segment. Okay, so the parabola looks like this. Where the maximum is here. Okay? Because that's where the shear force is 0. It must be. And then let me move this. Then finally, oh, sorry, this is, it must, like this. And then finally, from here to here, well, we can see this quite easily. I will not do any calculation, but see, if I cut here and look right, the shear force is constant, is By. That's the only force that is there. So the shear force is constant, and it's minus By. And minus By is exactly this number here. So this is how the shear force diagram looks like. And this is the linear part of the bending moment that should connect to this. There you go. So you have line, parabola, line. And here you have constant, line, constant. Now, Joe asking, how do you know how high the parabola is? Well, you have to actually find. So you have to find this point first. What's this point here? How do you find this point? Well, this is V of x. So I can find V of whatever equal to 0. So I can find whatever that is. So if I set this function equal to 0, I can find x. Solve for x. And then you find exactly that this x here is this x. Okay? And now that you are here, now that you know this x, let's call this x star. This is x star. And so you can do this value here. You can find this value here is m of x star. Okay? Because that's where you are evaluating the moment equation at that specific point. And you know for certain that is the maximum of the parabola. How do you know it's a maximum and not a minimum? How do I know that? Because this parabola has minus x squared. So minus x squared is a parabola that looks like this. Plus x squared is a parabola that looks like this. So a parabola that looks like this has a maximum point. A parabola that looks like this as a minimum point. Okay? So I can know all these things by just doing a bit of calculus and geometric considerations. Okay, so I think that's it. Let's solve. I would like to solve this one as well, but I'll do this later, or if not, I'll just giving you the solution. I would like to solve instead the 3D stress one. So let's start with question 1 very easily. Well, I don't know. Thank you, Joe. If that's not sure that's a compliment though. So this is 3D stress transformation. And this is question 1. I will not do all of them. I will not do all of question 1 because it's just basically the same thing all over and over. The Cartesian components at a point, let's do question 1. So question 1a is easy because you just have to use the equations that I gave you last time. So if you look at the lecture notes, these ones. If you look at the lecture notes, I told you, I told you about the compliance equations, which let you calculate the strain state given a stress state, and the elasticity equations that let you back up the stress state if you know the strain state. And this is what I'm asking here. So I don't want to do this because it's just a matrix multiplication. So just as long as you know how to find the, how to remember these elasticity or compliance equations. In this case, you want to find the stresses given the strains. So you need elasticity equations. In this case, you need to find the strains given the stresses, and then you need compliance equations. This is extremely basic, so I don't want to solve this one, but I do want to solve this one. The Cartesian component at a point are given here. We want to calculate normal stress and shear stress acting on a plane whose normal makes an angle of 48 degrees with the x-axis. So this is a bit more involved, remember? So let's do question 1c. Question 1c, I'll draw, first let me see if I can do this. Question 1c, this one, yes. So bear with me a bit because I have to copy all these numbers in. So I'll copy this I'll copy this already in a matrix. That matrix is the stress state. So the matrix sigma. Remember, the matrix sigma has all sigma x, y, and z on the diagonals. So the diagonal elements are minus 40. So this is minus 40 times 10 to the power of 6 newtons per meter square. So it's minus 40 megapascals. So let's say everything here is in megapascals. So we deal with better numbers. So this is minus 40. The second diagonal element is 80. The third diagonal element is 120. Then we have tau xy, tau xz, tau yz. Agreed? So tau xy is this one here. Tau xy is 72. And of course, you have the symmetric part as well, because tau xy is the same as tau yx, which is this element here. For equilibrium reason, they must be the same. Then we have tau yz, which is this element here, and this one. So tau yz is 46. And of course, we have 46 for tau zy. And then we have tau zx, which is this one, 32. And of course, it's also tau xz, which is this one, 32. Now, first of all, every time I have this, I also want to show this on an infinitesimal. Why? Because it's important. And because I will ask it to you at the exam as well. So that's why we do this on the infinitesimal. So let's say this is the x-axis. Again, it doesn't matter how you orient it. That's the whole point. This is the y-axis. And this is the z-axis. Now, this one, these red ones are the sigma x. So minus 40, that means it goes inside. Okay, so it's a compressive stress in the x direction on the x face. This one is called sigma x, but sometimes it's also called the sigma xx. Just to tell you, it's a normal stress on the x face in direction x. And so, of course, you have another on the back. I will not draw them in the back because otherwise the picture gets very cluttered. So I want to show what's going on here first. Then this one, I'll show this in green. And this is tau xy. So this is the shear stress that lives in phase x, so in this phase here, in direction y, which is this direction here. It's a positive 72, so it means it goes in direction y, and it's 72. And of course, there must be another one that goes like this. And this one is tau yx. Do you agree with me? This is this and this. 72, 72. They must be the same. And this, look at this. This is tau that lives on the face y. This is face y and goes in direction x. Then we have the blue one, this one, tau xz. So lives on the x face, but in the other direction, z. And this is 32. And of course, we have another one here that must meet it, which is also 32. Because it's this one here, and it's tau zx, lives on the z face in direction x. Are we allowed to use multiple colors in the exam to make it easier to read? Of course, I encourage you to use multiple colors so I have an easier time to mark. Just don't use too much red pen, because if we need to make any corrections, we will be using red pens. Okay, so don't use red at all if possible. Use other colors. Last one, let's make this orange. So this is tau yz, so it's tau in the y phase, which is this one, direction z. And this is 46. And of course, we have another one that must meet it at the edge. See, they always meet each other or they go away from each other. I'm only left with the 80 sigma y and the 120 sigma z. Okay, so this is the state of stress that I'm looking at. Do you agree with me? Good. Now, the other thing I'm asking here is to calculate the normal stress and the shear stress on a plane whose normal makes an angle of 48 degrees with the x-axis and 61 degrees with the y-axis. Now, remember what is that normal thing? So the normal is a vector of L, M, N, and these are also the director cosines of the normal. Cosine of alpha, cosine of beta, cosine of gamma. What are alpha, beta, and gamma? These are the angles. So asking what is 32 again? 32 is tau xz. This one, tau x. So this is tau zx. And this one is tau xz, which of course are the equal and opposite. Okay? So not opposite, just equal, because it must be symmetric. LMN, cosine of alpha, beta, gamma. And then we have alpha is 48 degrees and beta is 61 degrees. Okay, so I know that this one, can I find, so I know L. L is, so let me do this with the help of MATLAB as well. I'll call this N because I don't know it. And I'll say that cosine of 48 and cosine of 61. So cosine of 48 and cosine of 61. So these are 0.669, 1, and 0.4848. Okay, that's what's going on here. Can I find N? Remember, I told you that N is a unit vector. See, there's this little hat. Unit vector means that the norm of N is the square root of L squared plus M squared plus N squared, which is equal to 1. Unit vector. That's what it means. And so that means that we can find N. N, not N hat. N hat is the normal itself. N is this third element of N hat. N is just 1, sorry, the square root, sorry, N squared is 1 minus L squared minus M squared. So N is just the square root of this. Agreed? So let's find N equals square root of 1 minus cos d 48 squared minus cos d 61 squared. There you go. N is 0.5632. Okay, now we have LMN. We have a complete description of the normal vector N. How do we find the shear stress? So let me do this. L equal, because this is L. Yeah, let me clear all first. So this is L. This is M. And this is N. Okay. And now let's find the vector N, capital N, is LMN as a column vector. Okay. Now I have to multiply this times sigma. So sigma is a matrix. And that matrix is minus 40, minus 40. I mean, you can use MATLAB for this, of course. 72, 32, 72, 80, 46. If I'm getting anything wrong, you let me know, okay? 32, 46, and 120. Yeah, looks fine. And so I can just multiply. So I can find S first. Remember what was S? S is that vector that is not quite normal. So this is the projection of the tensor onto the plane of the normal, and then we project. You just find it here. Let me see. Go down. This is S. See, n times t. That's it. And n times sigma gives you S. This S is this vector here that was neither the normal stress nor the shear stress, was the composition of the two stresses. Since we want to find sigma n already, let's use this one straight off the bat in MATLAB. And you can find this by doing n times n times sigma times n times n. And this is sigma n. 134.92. Okay, so let me write it down here. Sigma n is n transposed times sigma times n. And this is a number. How do I know this is a number? Why is this not a matrix or a vector? Well, this is a 1 by 3. Remember, this is a row vector. So this one is a 1 by 3. This is a 3 by 3. This is a 3 by 1. So the result of this times this gives me a 1 by 3. And the 1 by 3 times a 3 by 1 gives me 1 by 1, which is a scalar. And so I get a scalar, and that scalar is 134.92 megapascals, of course, because we are working in megapascals here. And what is the shear stress? Well, the shear stress needed that S. So we jumped one step, and we shouldn't have. So let's call this resultant. Resultant is just this. These are the components of the resultant. And so in order to find tau n, we need to do the resultant squared. So the square root of the resultant squared, resultant times resultant. So this is row times column, like this, minus sigma n squared. Now, sigma n is a number, so I can just square it like this. You can't square a vector. In order to square a vector, you need to use this. So it's A times A transposed, which is the scalar product of a vector with itself. This tau is 87.23. Tau, I did down here, tau n is the square root of S squared minus sigma n squared. And that's 87.24 megapascals. Any questions? No questions? That's it. See, it's not very complicated. It's just using the formula, really. It's not much complicated. As long as you know what it means. Because I might be asking you things in words rather than in formulae, and you should be able to understand what I'm asking you. But that's the most complicated thing, probably. Because once you know what you're looking for, it's just a matter of using the formula sheet. Okay? All right, let's do the other one. This one, which is the most complicated one. Where is it? I lost it. So this one I don't need. This one I don't need. This one. No, not this one. Where is it? Oh, this one. Question 2. So we do have a stress tensor. We do have a stress tensor in megapascals. Where is it? No. In a 3D system, so this is question 2. So question 2. So let me write the stress tensor first. Sigma equals 30, 10, 10, 10, 0, 20, 10, 20, 0. So how does this look like? Let me sketch it very briefly. This is 30, sigma x, 0, 0. So there is nothing in sigma y and sigma z. This one is, let's do this in blue. This is tau xy. And so we have this one, which is tau xy, 10, which of course is also this one, tau yx. Then we have the orange one is tau xz, which is this one, which is also this one. And then we have this last one, let's do this in green. This is tau yz, and it's tau yz, it's y in direction z, which is this, and it's also this. And this is 20. Agreed? That's how it looks like. Now, confirm that one of the principal stresses is 40 megapascals, meganewton per meter squared. And find the other principal stresses and the direction cosines of the planes on which they act. In fact, you have to find eigenvalues and eigenvectors. So you need to find the eigenvalues and eigenvectors of this system. Remember, the eigenvalues are the principal stresses, and the eigenvectors tell you the directions on which these three principal stresses act. So how you have to orient this cube in space in order to find those three principal stresses. All right, so this is an eigenvalues problem. So part A is about an eigenvalues problem. And the eigenvalues problem looks like this. Sigma minus lambda I times x equals 0. This x is capital X. And this 0 is a vector 0. So these are the eigenvalues. And these ones are the eigenvectors. Now, instead of using MATLAB, let's do this by hand. Okay, so I'll show you once how to do this by hand. It's always in the same way, so you don't need more examples of this because it's always the same way. So first of all, let's calculate this matrix here. So it's sigma, which is this matrix here, minus lambda on the diagonal. So let's draw this one. Let me copy this one. So the matrix lambda sigma minus lambda I is sigma minus lambda I. This matrix is 30 minus lambda, and minus lambda. You agree with me? Yeah, that's easy. And now we need to find the characteristic equation. Characteristic equation is the determinant of this matrix equal to 0. It's an equation, and it's called characteristic equation. So how do you find the determinant of a 3 by 3 matrix? Now, there is one way, which is called the Sarrus method. Do you know that? You probably should know that. So if you just copy and paste the first two columns here, you take the sum of the three main diagonals minus the sum of the 3 off diagonals, which is this one. Okay. So it's the sum of this times this times this, plus this times this times this, plus this times this times this, minus this times this times this, minus this times this times this, minus this times this times this. Remember that? Have you done this anywhere? Sometimes in your lives? Yeah, okay. Okay, but I don't like it because it's a trick. Okay. What I like is the real thing. The real thing is because this only applies to 3 by 3 matrices. If you have a 4 by 4, you can't use this. So in order to find, to do the real one, we have to first of all sign all of them, each element, with an alternating plus or minus pattern. And then we choose, this is called the Kronecker delta. Okay, if you ever heard this term sometime, no? Okay. Kronecker delta. And then you have to choose a column or a row, it doesn't matter. Let's choose the first column. Once you have chosen the first column, the determinant is the first element, so 30 minus lambda, times the determinant of the submatrix that you find by removing row and column where this element lies. I'll give you 1 second to wrap your head around this. 30 minus lambda times the determinant of the matrix that I find by removing the row and column where 30 minus lambda lives. So times the determinant of minus lambda, 20 minus lambda. And that's the first step. Then we have to add, well, in this case, well, this is the first element. Now on this column, there is another element. There is minus 10. So minus 10 times the determinant of the matrix that I find by removing row and column where 10 lives. So this matrix here is 10, 10, 20 minus lambda. And then we have the last one, which is plus 10 times the determinant of this matrix here, the top left, top right corner, 10, 10, minus lambda, 20. So this determinant must be equal to 0, this thing. Do you remember how to find the determinant of a 2 by 2 matrix? Yes, this minus this. So let's do this. It's 30 minus lambda times lambda squared minus 400. Do you agree? Minus 10 times minus 10 lambda minus 200. Minus 10 lambda minus 200. Plus 10 times 200 plus 10 lambda equal to 0. Okay, now we just need to do these multiplications. And so I get, this is 30 lambda squared, 30 lambda squared, minus 12,000. So I'm doing this times this, and this times this. And then I'm now doing this times this, and this times this. So minus lambda cubed, minus 400 lambda, sorry, plus 400 lambda. And then we have plus 100 lambda minus 2000, sorry, plus 2000, plus 2000 again, plus 100 lambda equals 0. And now I have to just collect all the same coefficients, which are So let's start with the lambda cubed. Lambda cubed is this, only this. Lambda squared is this and only this. And lambda, just lambda is this, this, and this. Okay, so let's collect them all together. We end up with minus lambda cubed plus 30 lambda squared, 400, 500, 600 lambda, plus 600 lambda. And this is minus 12,000 plus 4,000 is minus 8,000 equals 0. This is the characteristic equation. See how fun is this? Imagine this at the exam. Imagine this having 2 hours for the exam. You have 4. Okay. 2 years ago, your colleagues had 2 hours to do the same thing, and no MATLAB. Okay. As this is called characteristic equation. All right. Now, confirm that one of the principal stresses is 40 megapascals. How? How do we confirm this? Well, if 40 megapascal is a principal stress, the principal stresses are the roots of this polynomial. So are the solutions of this equation. How many solutions does this equation have? It's a third order equation. It's got 3. So that means that if I take minus 40, if I say minus 40 cubed plus 30 times 40 squared plus 600 times 40 minus 8,000, this must be 0. So we can check this. Well, you can check this, that if lambda equals 40, then minus 40 cubed plus 30 times 40 squared plus 600 times 40 minus 8,000, this gives exactly 0. So checks out. Okay, so this is what I say. This is what you have to do if I ask you to confirm that one of the answers is a principal stress. So you just substituted it into the characteristic equation, it must be 0. Now, of course, this is 40, it's an integer number. If I'm asking you to check if 40.32 is a solution, that number is likely rounded off. That means it will not get exactly 0, but you'll get a number very, very close to 0. So if you get 0.1, let's say it checks out. Yes? How did I get minus 8,000? From minus... Did I miss anything? I don't think I missed anything. It's 2,000. Yeah, so it's minus 12 plus 2 is minus 8. Yeah, this is minus 12,000 plus 4,000. This is minus 8,000. Oh no, it's not 20,000. Oh, so sorry, that's my mistake. So it's 2,000. Yeah, 2,000. Okay. All right. So we did part A. No, we did part of part A. We need to find the other 2 principal stresses. How do we do that? You can do this with MATLAB. You can do this with Wolfram Alpha. You go here and say minus x cubed plus 30x squared. I'm using x instead of lambda because it's easier to write. Okay, plus 600x minus 8,000 equals 0. You just write the equation, and Wolfram Alpha spits out all the solutions. See, this is the cubic polynomial, and it has 3 roots. So it passes through the x-axis 3 times. At minus 20, this should be 10. And at 40, see, that's 40. So minus 20, 10, and 40 solutions. Okay, you can find this easily. But if you want to find this by hand, how do you do this? Well, since you know one of the solutions already, you can recur to the polynomial division. Do you know about that? Do you know how to make divisions with numbers? Elementary school, you did learn how to divide numbers. It's exactly the same with the polynomials. And then I'll show you how to do this. So what I'm saying is that if lambda is a solution, so if 40 is a solution, if lambda equals 40 is a solution, that means I can rewrite this thing is equal to lambda minus 40 times something something. Okay? So I can split, I can find this something something by dividing this one by lambda minus 40. Remember the minus here. The solution is 40, but you divide by lambda minus 40. Okay? Because in the equation, lambda equals 40 is lambda minus 40 equals 0. Agreed? That's how it works. So how do you divide this by that? You just use the easy polynomial division. Well, let's go. So how do we get rid of lambda cubed here? If I multiply this times minus lambda squared, I can get rid of lambda cubed. How? Because this times this gives me minus lambda cubed plus 40 lambda squared. Do you agree? So this times this gives me this. Now, do you remember how you did the division in elementary school? What do you do now? You subtract this one from this one. So this minus this gives you 0. So this goes away. And this is 30 minus 40 is minus 10 lambda squared plus 600 lambda minus 8,000. Agreed? That's it. Now, how do we get rid of this 10 lambda squared? Well, I multiply this times minus 10 lambda. Okay? So if I multiply this minus 10 lambda, I get minus 10 lambda squared, and this is plus 400 lambda. Do you agree? You should. And then I do again subtraction. This is 0, and this is 600 minus 400 is 200 lambda minus 8,000. How do I get rid of 200 lambda? I multiply this times 200. So plus 200. I get 200 lambda, and this is minus 8,000. There you go. There is no remainder. No remainder. No remainder means that this is exact solution. So remember when I told you that this equation is equal to lambda minus 40 plus something something, that something something is this. So this times this gives me this. Okay? Exactly like a division. Now, a solution is this. The other one, well, the other two are here. How do you solve this? You solve it in the usual way by doing minus lambda squared minus 10 lambda plus 200 equals 0. And this is just 10 plus or minus the square root of b squared minus 4ac plus 800, 4ac, okay, divided by 2a. And this is equal to 10, so this is 900, the square root of 900 is 30. So 10 plus 30 is 40 divided by -2 is -20. So sigma 1, so sorry, let's call this lambda. Lambda 2 is -20. Lambda 3, because this is lambda 1, okay? Lambda 1 is 40. Lambda 2 is -20. Lambda 3 is 10. Minus 30 is -20 divided by -2 is +10. And now we have to order them. So sigma 1 is the smallest. And the smallest is -20 megapascals. Sigma 2 is the intermediate one, which is 10 megapascals. No, sigma 3 is the smallest, guys. No, sigma 2 and sigma 1 is the largest, which is 40. Okay, so lambdas are the solutions and they can be in any order. The sigmas must be in order. Does it make sense? Do you agree? Good. Now, how do we find the eigenvectors? Because, well, this is part A, and that's done. How do we find the eigenvectors? The eigenvectors are found, remember, sigma minus lambda I times x equal 0. Now, for any lambda, you have an associated x. Now, we have found all the lambdas. We didn't find any of the x's. How do we find the x's? Well, if you want to find x1, you need lambda 1, well, let's say sigma 1. So if you remove sigma 1 from the diagonal, rather than any lambda, you find x1 by solving this. These are three equations. Remember, these are three equations in three unknowns. Actually, these are three equations in two unknowns, because we made sure that this determinant is 0. So we have an overabundance of equations with respect to unknowns. So let's, well, let me copy this, because this also applies to sigma 2 and sigma 3. So we have sigma 2 and sigma 3. So sigma 2 to find x2, sigma 3 to find x3. Now we want to find all three. We want to find all three, the three principal directions. I'll show you how to find one, and you can find the other ones. So how to find the first one? Remember, x1, this vector here, is 1, A1, B1. And the unknowns are A1 and B1. Or you can also say ABC. A1, B1, C1. Just so you know that you have infinitely many solutions. So you only need to find A and B. Then C will be a function of A and B always. Let's see how it checks out. So first of all, I have to draw this matrix again. This one. Let me copy this. Now, at the exam, if you're doing this on a tablet, you can also do this exactly as I'm doing it, and then print a PDF and submit that PDF. Okay, if you do this on a tablet, so you don't need to actually use the whatever that is given. So or you can type the answers, or you can scan the pages with a. I mean, you've done this last year, haven't you?
Could we not like just screenshot it and then put it on?
Yeah, exactly. Yeah, you can do that. But I mean, if it's easier for you to just do print PDF and send it, don't worry. I mean, as long as it's readable and it's in PDF, that's fine. Okay. But if you're not using the university template, you must make sure that on the front page you have all the information that is found on the template as well. So your SID, your name, your full name, SID, what are you attempting, all the questions that you have attempted, they are on the front page, and they've also be found on the front of your PDF as well. Okay. So this is 30 minus 4. Remember, the sigma 1 is 40. So this is minus 10, minus 40, minus 40. Agreed? So this is the first one that we need to find, the first one. And this is times A1, B1, C1 equal 0, 0, 0. Agreed? This is the equation. I mean, it looks scary, but these are just 3 equations into unknowns. Okay, so it's even easier. So this thing boils down into this. And so how do you put this in system form? This is always. So in system form, this looks like minus 10 A1 plus 10 B1 plus 10 C1 equals 0. That's the first equation. This times this, plus this times this, plus this times this equals this. The second equation is this times this, plus this times this, plus this times this equals this. So 10 A1 minus 40 B1 plus 20 C1 equals 0. 10 A1 plus 20 B1 plus minus 40 C1 equals 0. And now let's solve this. And this can be easily solved by taking, say, if I take, let's say this is equation 1, equation 2, equation 3. If I take, say, 2 minus 3, I mean, this can be solved in many ways. So 2 minus 3 is easy because I get rid of A1. So 2 minus 3 is this minus this, 0. This minus this is minus 60 B1. This minus this is plus 60 C1 equal 0. And that means that B1 equals C1. Okay? So I know that whatever I put into the spot B1 must also go into the spot C1. On this vector here, these 2 numbers are the same. And now let's see what is the relationship between any of these and A1. How do I do that? Well, now that I know that B1 is C1, I can just put it here, whatever. Say I put it into equation 1. If I put it into equation 1, I have minus 10 A1 plus 10 B1 plus 10 B1 again equals 0. And so I get that minus 10 A1 plus 20 B1 equals 0. And so I get that A1 is, sorry, let's do B1 as a function of A1. B1 is 1/2 of A1. Okay? And that's it. So I can only get these 2 relationships. And so the final vector x1 is whatever A1 is, B1 is always 1/2 of A1, and C1 is equal to B1, so it's also 1/2 of A1. Okay? And now that I have this, I can get rid of A1 as well. Because it doesn't, I told you I have infinitely many solutions. And these correspond to the infinitely many lengths this vector can have. I'm not interested in the length of the vector. I'm interested in the direction of the vector. So let's just get rid of A1. Okay? This is one description of that vector. I don't like 1/2, 1/2. Let's multiply everything times 2. So the other description of this vector is 2, 1, 1. That's perfectly valid. Okay? Or I can say 4, 2, 2. Doesn't matter. Or -2, -1, -1. It's the same. So they are the same up to a scale factor. Now, question, is this a unit vector? No, because one component is 2 already. So it can't be a unit vector. Can we make it a unit vector? Yes, because what we wanted to find now is the director cosines of this vector here. So first we make it a unit, so rescale it down to a unit vector. And then the components of the unit vector, I told you already, are the director cosine of that vector. So the cosine of alpha, cosine of beta, cosine of gamma. So let's make x1 a unit vector. So I need to find the magnitude of x1, which is equal to the square root of 2 squared plus 1 squared plus 1 squared, which is equal to the square root of 6, 4, 5, 6, yes, square root of 6. And now that means that the unit vector x1, I'll do this with a hat, means unit vector, is 2 divided by the square root of 6, 1 divided by the square root of 6, and 1 divided by the square root of 6. And let me do this with MATLAB. So 2 divided by the square root of 6 is 0.8165. One divided by the square root of 6 is half as that, 0.4082, which is the same, of course, for C. And these ones, coincidentally, well, not coincidentally, it's on purpose. These ones are also LMN of this vector. So they're not the original LMN of our other normal. And so that means that these are also cosine of alpha, cosine of beta, cosine of gamma. And so the question that says, what angle does the x-axis makes with the principal directions? Now, this is the first principal direction. So the first principal direction makes an angle alpha with the principal. So let's call this L1, M1, and 1. This is alpha 1, beta 1, because you have this x1 only. Then you have to do the same for x2 and the same for x3. So alpha 1 is the inverse cosine of L1, which is equal to L1 was 2 divided by the square root of 6. So the inverse cosine in degrees of this number here is 35.26 degrees. Any questions? It's 4 p.m. I'm done with the tutorial. There's probably people waiting outside. So if you have any questions, you let me know, because I don't know if probably we need to make the other people enter. So I'll stop recording now.